Chapter 16, number 38. So you got dogs, the cost of medical cost for dogs is distributed normally with a mean of $100. What is this, annual cost? Let's see. Annual, right? $100 and $30. And for cats, the annual cost is a normal distribution of $120 and $35. Okay, so the first question is, what's the expected cost, the annual cost for a dog and a cat, right? What's the expected difference, the expected difference in medical care for a dog and a cat. So the expected difference, we could symbolize that by delta or whatever, equals the expected value of cats minus, we could do it either way. You can do dogs minus cats or cats minus dogs. So cats, I just want to keep it positive, so cats minus the expected value of dogs is going to equal $120 minus $100, which is $20. Now if you do the other way, the difference would be negative 20. Okay, B, what's the standard deviation of that difference? So the standard deviation of the difference, and again I'm using the Greek symbol delta to stand for difference, the Greek letter D, is going to equal the standard deviation of the variance of the dogs, which is 30 squared, plus the variance of the cats, which is 35 squared, and that equals approximately equals 46.1. And you can see that I have that on the calculator right here. Okay, there's it is on the calculator. All right, so C, if the cost can be described by the normal models, what's the probability that medical expenses are higher for someone's dog than their cat? So C, we're going to draw a picture. So we want to know when the difference is 0 or less. This is difference of cats minus dogs. Okay? And that difference happens to be $20. Now over here is the difference is 0. So we want to know how often the difference of cats minus dogs is less than 0. What's the probability that that happens? Okay, so the average difference is $20. We want to know how often it's less than 0. So first we'll find the z-score. Z equals y minus mu over sigma, which equals 0 minus 20 over 46.1, which is approximately equal to 0.434. Again, you can see that on the calculator. I've done it over here. Okay, and then I'm going to use the picture here. I got minus 99. This is the z-score of the end of the tail, and the z-score for 0 is 0.33. I'm sorry, 0.434. Negative 0.434. So I will use normal CDF to find the probability of getting a z-score that's smaller than 0.434. And so I do normal CDF, which is second, and then vars. Normal CDF is 2. And I'm going to go all the way to the end of the tail. So that's negative 99. It always goes from left to right, comma. And I'm going to put in negative 0.434. Okay, close parenthesis. I hit enter, and I get 0.332 approximately. So the probability that the z is less than negative 0.434 is approximately equal to 0.332. Okay, so about a third of the expenses for dogs on an annual basis are higher than the expenses for cats. Last question, what concerns do you have? Well, there's a couple of concerns. First of all, the standard deviation is awfully high for this mean, and so there's a lot of variance here, which leads you to think, and this seems like it's true about medical expenses in general, not just for dogs and cats. It's hard to imagine that medical expenses are actually normally distributed. I mean, with a mean of $100, a cat can get sick or a dog can get sick, and you're going to be spending thousands of dollars. So it seems like the distribution would be skewed, and that would be one reason why you'd have a fairly high standard deviation. So that's a concern right there. And if you look at the distribution for $100, I mean, the standard deviation of 30. Well, it's just you can only go a little bit over 3 standard deviations to the left, but it's very easy to go many standard deviations to the right. It's certainly conceivable you could spend $500, $600, or $1,000 on an animal in a year, and probably quite a few people do. So that's the main concern, that they're not actually normally distributed, and that standard deviation is so big. That's it.